Welcome, everyone, and thank you for joining today's MDOT webinar. We are delighted to host Dr. Ziping Zhu, a postdoc fellow in statistics at Harvard University, working with Professor Susan Murphy. Many of you will recognize Professor Murphy's name from her foundational work in reinforcement learning and just-in-time adaptive interventions, both of which have fundamentally shaped how we think about digital interventions in health behavior change. Ziping's research lies at the intersection of reinforcement learning and mobile health, with a focus on developing intelligent adaptive systems for delivering digital interventions in real time. His work tackles one of the key challenges in the field, which is how to personalize support not just for individuals, but also within the social networks where health behaviors often take place. So today's talk will introduce an exciting new direction in this space. While most digital health interventions focus on individuals, many of the real-world behaviors unfold in social contexts, such as patient-caregiver dyads. Ziping will present on ADAPTS, an upcoming clinical trial using a novel multi-agent reinforcement learning framework to deliver coordinated, personalized interventions to both members of the dyad. This approach has the potential to significantly improve outcomes by harnessing the social dynamics that underpin health behavior. So let's dive in. Ziping, the virtual floor is yours.
All right, thanks Vivek for the introduction, and it's a great honor to have this opportunity to share one of our recent work on developing reinforcement learning for digital intervention deliveries in the dyadic setting. I'm Ziping Xu. I'm currently a postdoc fellow at Harvard University, and I will be joining UNC Chapel Hill as an assistant professor in the School of Data Science and Society. All right, before I dive in, I want to acknowledge the amazing teams I work with on this project. This includes my postdoc advisor, Susan, and a bunch of collaborators from Northwestern University, University of Michigan, Boston Universities, and one of our industry partners who specializes in the game design, which appears to be a very novel and interesting component of the intervention package. So this project is about a trial that is currently being developed called ADAPTS-HCT. You can see a logo here. All right, this is an outline of today's talk. I want to give a very brief introduction about what we do in the lab, and basically we use RL to develop personalized interventions. And why do we care about personalization this much in mobile health, and why are we interested in using RL? I think in the last lecture, Walter covered a little bit of this, and I will give some details about it. And then I'll talk about why we're interested in these social network structures. More specifically, we work on the dyadic structure, which is two individuals in a small social network. And what are the main challenges brought by this structure, and what are the opportunities? And then I'll briefly introduce the ADAPTS-HCT trial and the multi-agent reinforcement learning solution we proposed for this study. All right, so what we do is that we develop and implement online autonomous reinforcement learning algorithms. These algorithms are used to personalize digital intervention deliveries. For instance, you might have heard of a bunch of deployed studies. For instance, HeartSteps and Oralytics. HeartStep is a clinical trial where we use RL to decide if and when to send a message to encourage physical activities, and the Oralytics is an RL agent. It's a trial where we have an RL agent to send prompts to engage in healthy oral health habits. All right, so a personalization is a term that we talk a lot when we motivate the use of RL in the mobile health context. So when we talk about personalization, we actually mean that we want to adapt both the timing and the type of the support based on the person's changing state and the context. So this is really about to enhance the usefulness and responsiveness of digital interventions. And this is critically important because mobile health is such a dynamic situation where it's very hard to believe that a fixed deterministic strategy for intervention delivery could achieve a good treatment effect. For instance, there can be a lot of variabilities both between person and within person. So for instance, I'm using hard steps as an example. Some folks might prefer doing exercise during the weekends, and others might prefer to do it in the mornings before work during the weekdays. So these variabilities makes it it's important to adapt the decision rules for each person specifically. And also there can be strong variability even within the person over time. For instance, people's life situations could change. They might go through some unpredictable, stressful event which could change their regular life routine, which means that we need to adapt our decision rules based on those changes. So that said, personalization really requires us to make decisions that evolves both within a person over time and between person. And so it's very difficult for us to manually design those very dynamic decision rules ahead of time. So that's why we really need a data-driven framework to achieve this level of personalization. So this is the reason we are interested in online reinforcement learning. So reinforcement learning is a great tool for this because it allows us to learn and update a policy that interacts with an environment in real time. So there are three core pieces in reinforcement learning. The first one is the state. A state variable is all the information that an agent might concern to make a good decision making. And the action AT here, in our context, it is the intervention. So often we have a binary action space, meaning that at the specific predefined decision time, the agent needs to make a decision about whether to send a notification or not. And the reward here often is the health outcome that we care about. For instance, step count or the medication adherence, which is the main health outcome we care about in ADAPTS-HCT study. So the goal here is that we, generally speaking, the goal is that we want to maximize the cumulative rewards or the cumulative sum of health outcomes we care about. So this is a closed loop interaction process. As you can see, the AI agent interacts with users by sending them actions, and the users respond to those actions or interventions, which generates the next reward and the next state. Okay, so and specifically, what we implement is an online RL versus offline RL. So online RL means that we deploy an agent that dynamically learns in an unknown environment through real-time interactions with users. And this really allows us to personalize based on the real-time user's own data. And this is also often called learning to treat. And it is also important to note that our algorithm is part of the treatment, resulting in personalizing genotype. We call it p-genotype. So RL is not just used for adaptive experimental design, it also significantly affects the treatment effect, affect the effectiveness of the intervention package. So it is an important component of the entire intervention package we designed here. All right, so in the previous p-genotype studies, RL has been successfully applied in many of the previous studies, and they have been shown to be very promising. But most of these studies treat each person as independent. There is no social connections among participants. And the participants are, so the transitions of participants are actually independent, conditioned on the sequence of treatments. However, we are motivated to study people's living in the same social network and start to intervene people living in the same social network. One of the previous meta-analytic review shows that social relationships, in fact, appears to be a major determinant of health. So this really motivates us to start to design intervention packages that actively intervene all the people living in the same social network, so we can leverage these social connections. So for instance, to make things more clear, previously we have a single target person and we design an intervention directly targeting at this person. But now we're moving towards the direction where we have where we target at the entire social network with a targeted person and other participants centered around this person. They can be the care partner, they can be fellow patients, they can be doctors, and we have interventions targeting at all these individuals. But the goal still stay the same. We want to support a targeted person's health outcome, right? So a starting point would be this dyadic structure. A dyad is a very small social network with two individuals, and in the health settings, often one individual is the target person, the patient, and the other individual is the care partner. And their relationship, in fact, plays a very important role in this dyadic setting. And we often have three type of interventions targeting at different components in this small social network, in this dyad. All right. So as an example throughout this talk, I'm going to introduce this ongoing mobile health clinical trial called ADAPTS-HCT, and it exactly have this dyadic structure. So in this study, the study population is adolescents and young adults. We call them AYA. They had undergone bone and marrow transplant, and they need to take, after this surgery, they need to take medication on a twice daily basis over 100 days in order to prevent graft versus host disease. And because those are very young people and they are very sick, we have interviewed with a number of patients in this population. Often after this very severe treatment, they can have a very short memory and they can barely have the ability to take care of themselves. So that's why their care partner plays an important role in terms of managing the medication, the medication adherence, and making medical decisions. And they're also responsible for caregiving in the AYA's daily life. And this population, in fact, are going through a lot of stress, as you can imagine, because the care partner, often their parents, they have to balance the caregiving jobs and their regular daily jobs, and to be able to provide good caregiving. So that said, the goal of this study is that we want to develop digital interventions to enhance AYA's medication adherence. All right, so a bit more details on the interventions we designed for this dyadic structure. We in fact has three types of interventions specifically targeting at three components in this dyad. And our AI agent is making decisions about whether those digital interventions will be delivered at a specific time point. So first, on a twice daily basis, we will send personalized messages to AYA. So those messages are designed to help with positive emotions. And secondly, on a daily basis, we also send messages to the care partner. Those messages help them to improve their self-care strategies and build up positive emotions as well. So a novel part about this trial is that on a weekly basis, we in fact ask AYA and the care partner to play a collaborative game. This is in fact a puzzle game. And this game is designed to provide an opportunity for AYA and the care partner to work together and to build up relationship quality. All right, so to give an overview of what RL does in this study, as we mentioned, this is a closed loop interactions between agent and the dyads. So the agent at a predefined decision time it makes decisions about whether or not whether a digital intervention is delivered. So we have three types of interventions, and they are in fact delivered at three different time scales. So for all the decision time, we have messages for AYA, and on a new day, we have messages for the care partner, and on a new week, the agent decides whether we set this week to be a game on week or game off week. When it is a game on week, the game will be available for the dyad to play. When it is a game off week, the game the dyad won't be allowed to play the game. And the dyad will generate some of the observations that will inform the future directions for the RL agent. For instance, we use EMA to measure relationship quality, and some of the variables like care partner psychological distress and their positive effect about their life, and some other variables that we believe are relevant are time of the day and the recent dosage and the app burden. And the primary outcome, which is the current adherence, will be self-reported by AYA on a twice daily basis. So those are the primary outcomes our agents is trying to optimize. To make things a little bit more concrete, so this is an example interaction flow between the AI agent and the two individuals. As you can see, over a sequence of decision times, the AI agent would decide whether to prompt the users, and the users, we use EMA to collect some of the variables from both the care partner and the AYAs. And on the new week, the agent would also decide whether to set the current week to be a game on week versus a game off week. All right. So before I talk about the algorithms we designed for this study, I want to emphasize some of the challenges brought by both the typical mobile health studies and also the new challenges that arise from this dyadic setting. So the big picture is that we want to maximize the cumulative rewards, which is the medication adherence over 100 days. And it is important to know that our goal is that we want to learn as fast as possible so we can benefit more participants, right? So we're not in a setting where we have infinite amount of data, so we can take forever to learn a good policy. In fact, those are typical challenges from mobile health. In fact, we only have a very limited sample size. In this pilot study, we have 25 dyads. And as we all know that we're learning based on human behaviors, and the human behaviors can be extremely noisy and also non-stationary. You know, a lot of decisions are made based on variables, based on the variables that the agent cannot observe. So this is a very challenging learning setting. So it is important to trade off between bias and variance so our agent could learn as fast as possible. And some of the challenges arise from this dyadic setting. So first, we have multiple interventions versus a single intervention. So this immediately means that we have a higher dimensional space in the policy space, which makes it more difficult for the agent to learn. And another feature about this study is that the different type of interventions are in fact chosen at different time scales, which requires the agent to be designed to so that it is coherent to this different timescale structure in the study. And some of the interventions may only have a very distal effect on the primary outcome. So meaning that our system is in fact very asymmetric. For instance, this is an example causal pathways about how a care partner's message can eventually affect AYA adherence. So think about the message sent to the care partner, because those are positive psychology messages, they're likely to reduce care partner psychological distress, and the reduced psychological distress may in long run improve relationship quality between the AYA and the care partner. And in long run, it could eventually increase AYA adherence because a better relationship makes it easier for the care partner to provide caregiving. Right. So you can see that the intervention effect of the message sent to the care partner, in fact, has to go through a very long causal causal pathway in order to affect AYA adherence. So along this causal pathway, there can be a lot of noise when generating the variables in this process, which makes it very challenging for the care partner to be able to learn a good policy. All right, so those are the challenges, and what we do in this study is that we try our best to incorporate domain expertise. More specifically, we ask our science team to guess about the major effects between the mean variables, and we encoded those causal effect, those major causal relationships as a causal dyadic cyclic graph. We call it causal DAG. So what causal DAG about is that it encoded some of the conditional independence structure between the variables that we care about, and so we can leverage those informations from the causal DAG to accelerate the learning. So this part is based on a recent paper we published at the AIME, AI for Medicine, about this study. So before I go through the details about the causal DAG, I really want to emphasize here that real-world causal relationships are in fact likely to be super complex. Direct causal pathways can exist between any two variables. This is the complexity level of the real world. But what we want from the scientific team is that they guess about the major causal pathways that we believe are more detectable given the noise and the sample size. So everything is a bias-variance trade-off process. And these guesses could help us understand the primary causal pathways that the interventions may take to affect the AYA adherence, so we can design agents that focuses on those primary causal pathways. All right, so we can walk through some of the key variables in each components and our understanding of these causal relationships between those variables. For instance, in AYA, the decisions and the variables we observe are on a twice daily basis. So we have index W, which represents the current week, and this whole block represents a whole week. And the second index is a day index, and the third index is a binary index. When it equals to 1, it represents a morning decision time. And when it equals to 2, it represents an evening decision time. And there are 3 variables that we care about here. One is the AYA intervention. Those are the messages we send to AYA. And the AYA app burden, because trying to engage users in the mobile health study is a very important in order to achieve a good treatment effect. So when we prompt the users too much, they will feel burdensome to use the app, and in the long run, they will ignore the message we send to the users. So app burden appears to be an important moderator for the AYA intervention. And also we have the primary outcome, which is the AYA adherence. Those are the twice daily self-reported medication adherence. All right, so the care partner component, in fact, share a very similar structure here. The only difference is that we have care partner psychological distress as the immediate outcome of the care partner intervention. Those interventions are positive psychology messages that are designed to directly mitigate the care partner psychological distress. And the variables and decision makings are made on a daily basis, every day in the morning. And in the end, we have the relationship component. So here we have 2 variables here. One is the game intervention, which is a binary variable representing whether the dyad is allowed to play a game or not during the week W. And the relationship quality measured also at a weekly basis. So as you can see that the game intervention, because it is a higher level of requirement of engagement for the AYA and the care partner, we ask them to engage more in the mobile app to play the game. So it will in fact increase the app burden. And the game intervention, because it is designed to build up relationship quality, we believe it could increase the end of week relationship quality. And the relationship quality itself could potentially increase AYA adherence and decrease care partner psychological distress. So those are our understanding about the major causal relationships between a bunch of variables that we care about in this system. As you can see, those are super complicated causal relationships, and our goal is that we want to design an RL algorithm that is sample efficient, meaning that we can learn a good policy within limited samples. And the goal is that we want to incorporate those knowledges we learned from the DAG, and so that we can do a better job on bias variance trade-off. All right, so this plot appears to be highly complicated, and to better understand the knowledge from this causal DAG, let's talk about the main causal pathways about how an intervention could eventually affect AYA adherence. So the most direct causal effect is probably the AYA intervention that can directly increase AYA adherence, because those messages might make AYA feel better, so they're more likely to adhere to medication. And regarding the game intervention, there are two major causal pathways. So one causal pathway is that the game intervention can potentially will increase app burden because we ask the AYA and the care partner to engage in the game. And an increased app burden may decrease AYA adherence. So this is in fact a negative effect. But the game itself is designed to improve relationship quality, which can improve the end of week relationship quality, which can potentially increase the next week AYA adherence. So as you can see that this causal pathway is potentially more distal because it only affects the next week sum of the reward. And the causal pathway, as we discussed in one of the previous slides, is even more distal for the care partner intervention. It has to reduce the care partner psychological distress, and the reduce the psychological distress may increase end of week relationship quality, which affects the next week sum of the reward. So this causal pathway is very distal and can potentially be very noisy. All right, so let's talk about the algorithm design. How do we design the algorithm to incorporate this knowledge? So first, let's see that if we're gonna follow what we did in the previous studies, for instance, HARSTEP or analytics, we would have a flattened agent. This agent makes all three types of decision makings for both AYA, care partner, and the relationship component. So the issue is that this flattened agent makes it very difficult for us to account for those different causal pathways that different interventions may take. This is because our system is highly asymmetric. So it requires a corresponding asymmetric design on the agent to be able to leverage those causal DAG information. And on the social network, in long run, if we're going to scale the social network to a bigger social network with n nodes, potentially the action and state space may scale exponentially in n. But a flattened agent, because it has to make decisions about all the components, it must incorporate pretty much all the information in the system, which can easily make the problem intractable. So this is the computational challenge. And in the end, we really care about interpretability. We would want that the policy learned by the RL algorithm can be explained or interpreted by our domain scientist. But this is difficult for the flattened agent because the flattened agent always output a joint policy, and all the decision makings are in fact coupled. So it's very difficult to interpret and reason for the scientist. All right, to address these challenges, we propose a multi-agent RL algorithm. And as we can see from this causal DAG, relationship component really appears to be a bottleneck component in this DAG, meaning the condition on the relationship quality in the previous week and the game intervention for the current week, we can in fact decouple the AYA component and the care partner component, which motivates us to in fact design the algorithm so that we have three separate agents. Each agent is only responsible for one type of intervention decision making. So this naturally solves the issue from the multi-scale decision making, because we can simply set the frequency for different agents corresponding to the type of intervention components the agent is responsible for. So for instance, AYA agent only makes decision about the AYA intervention, and the care partner agent only makes decision for the care partner agent. All right. So this is before we talk more details about the specific design for each agent, let's talk about what are the base algorithm we would use for each agent to be able to learn and make good decisions. And this base algorithm is called RSVI. It is a randomized least square value iteration algorithm. So what RSVI does is that it approximates the action value function, which is also called the Q function in the R literature. So this Q function is in fact a prediction on the sum of the rewards given the current action and state value pair. So this is really about our prediction on how important and how valuable a specific action and state pair is. And we're approximating this function through a linear model. This is what RSVI does. And the parameters are computed by solving a Bayesian linear regression through an iteration. So with a Gaussian prior. And an important component about the online RL algorithm is that it must be able to do exploration. The exploration is about to explore the components of the environment that the agent has not seen yet. So for instance, if the agent does not know how to make decisions when burden is high, so the agent would try to increase the burden so that it can have some knowledge about how the system could evolve with a higher burden. So this is about exploration is critical to guarantee that the online agent could learn a good policy. So the exploration is conducted through sample a temporarily correlated noise on top of the solution solved by Bayesian linear regression. This noise is added to the Bayesian linear regression solution, which is theta bar here, and which we generate theta prime. So theta prime are the parameters for the action value function, which will be used to make decisions. All right, so why we're interested in RSVI? So first, it's an MDP algorithm, so it allows us to do long-term planning. And more importantly, this is a Bayesian framework algorithm, so it always induces a stochastic policy. A stochastic policy means that the action sampling probability are always strictly bounded between 0 and 1, which allows for after study analysis, because a lot of causal inference approach would need to compute a propensity score, and the propensity score will be unbounded if the action selection probability goes to 0. All right, so and also this is a Bayesian framework, so it allows us to incorporate some of the existing knowledges prior. For instance, we can compute some of the prior for our algorithm from the existing data set, and those prior can also incorporate some of the domain knowledge. And this prior will be used to warm up algorithms so we can learn more efficiently. All right, so what we do here is that we run an infinite horizon RSVI independently for each agent, and which means that we need to make a bunch of decisions independently for each agent as well. So those are the decisions that we're making. We're trying to optimize and make for each agent. So for instance, feature mapping, this is about to decide what are the relevant variables specifically for each agent. Because we're learning in a very challenging setting with a limited sample, so we really want to keep the model as simple as possible, but also we need the capacity to be able to capture the dynamic of the environment. And a second decision we make is the discount rate. Discount rate is about how long we would need the agent to look into the future when the RL agent is doing long-term planning. So the effective horizon is actually 1 over 1 minus gamma. And and third point is a reward function. As we will see later, that the primary reward is not always the best learning signal for the RL agent. So that's why often it's the case that we want to design a new learning signal for the agent to be able to learn as fast as possible. But the primary outcome of the study is always the sum of the medication adherence. And in the end, sometimes we have to make decisions about to what extent we want to pull the data across dyad. As we mentioned before, there's between person heterogeneity, which seems like we should not pull data across dyads. But because each dyad only have very limited sample, sometimes we want to accelerate the learning. So we want to extend to some extent, pull the data across dyad to be able to accelerate learning. All right, so in terms of the agent-specific feature maps, as we mentioned, relationship components appear to be a bottleneck component between AYA and the care partner, meaning that when AYA agent makes decisions, it could ignore all the variables from the care partner component, and the same case goes to the care partner agent. And the relationship agent often can incorporate all the relevant information. So by doing so, we get rid of some of the irrelevant variables for the AYA agent, the care partner agent. So the maximum feature dimension for those two agents can be significantly reduced. We're reducing this dimension from 8 to 4. Also, we're designing agent-specific discount factors. So discount factors is about how much do we look into the future. So for a specific discount factor, the goal of the agent in fact becomes a discounted sum of the reward into the infinite long future. And a high discount factor can in fact be used as a way of informing regularization, so we can trade off a good bias and variance. And in RL framework, the effective horizon, meaning how many steps you're planning into the future, equals to 1 divided by 1 minus gamma. So we believe that 1 week is a reasonable length of horizon for the RL agent to be able to do planning. So all agents, in fact, have effective horizon for 1 week. An AYA agent has 1 over 1 minus gamma AYA equals to 14, because 1 week has 14 decision points for AYA, and care partner has this effective horizon equal to 7. And for the relationship agent, because the decision is already happening on a weekly basis, gamma simply equals to 0, meaning that we can only deploy a banded algorithm for the relationship agent. All right, but even though we tailored those agent design specifically for each agent, there are actually some issues arise from this multi-RL multi-agent RL system. So the issue here actually is about the primary outcome appears to not be a good learning signal for the care partner agent and the relationship agent. So for instance, as we can see that there's no causal pathway from the care partner interventions to the current week medication adherence. This is because conditioned on the relationship component, care partner component, AYA component are independent. So this means that the primary outcome, in fact, provides no learning signal for the care partner agent to learn. And similar situation happens to the relationship agent. The banded algorithm does not account for the delayed effect of actions. So meaning that when the relationship agent is learning only based on AYA adherence, it will ignore the effect of the increased relationship quality that can potentially benefit the next week. So the issue arises from the fact that we use a smaller gamma to reduce learning variance, and which makes the situation such that we are no longer able to capture the delayed effect into the next week. So our solution to this is that we're gonna construct the surrogate reward for the care partner agent and the relationship agent. So let's go back to the causal deck again. we identify the mean mediators between the interventions and the reward in the next week. So we have, in fact, 5 variables that appears to be the mediators. So they are the relationship quality, AYA adherence, AYA burden, and care partner distress and care partner burden. So what we do is that we try to estimate the conditional expectation of the next week reward given those mediators. More specifically, what we do for the relationship agent is that among those mediators, we believe that the primary ones are the AYA adherence, AYA burden, and the relationship quality. So we fit a linear regression to estimate the following conditional expectation. This is a conditional expectation of next week sum of reward conditioned on all the variables the relationship agent observed in the beginning of a week. So those are the features for the relationship agent. And the surrogate rewards is simply becomes a 2-step approximation. The surrogate reward is the estimate of the current week sum of the reward plus the next week sum of the reward, and we take the maximum over the next week relationship game intervention choice. So this makes it, by constructing this surrogate reward, the bandit algorithm in fact is trying to optimize a 2-week sum of the reward instead of 1 week. So we account for the delayed effect of actions. And regarding the care partner agent, we in fact have an additional level of complexity. So first of all, the care partner agent, it affects the next week sum of the reward through the mediators, which is the end of the week relationship quality. And we believe that relationship quality will have a positive effect, only a positive effect on the next week AYA adherence. So we can simply add a indicator for the end of week relationship quality at the end of the care partner planning within 1 week. And this is often called a sparse reward because you get only non-zero reward in the end of the study, which is also very challenging to learn because this is also a distal signal. So an additional layer is that we attribute this sparse reward into different steps within 1 week. What we do is that we feed linear regression to estimate the conditional expectation of the end of week relationship quality given the care partner distress, care partner burden, and the current context, which are the actions and the relationship component variables. And the surrogate reward is simply this G function. All right, so you can see that we're trying to map the very distal sum of the reward in the next week first into the end of week relationship quality, and then we map the relationship quality to each day, which allows the care partner to have a signal to optimize every day on a daily basis. All right, so we have some brief idea about how to construct those candidate algorithms, and because healthcare setting is really a high-stake situation, so we really want to evaluate our algorithms carefully to justify our design decisions. So what we do is that we build a digital twin of the target population, and in a recent framework paper, we call this digital twin a Jetta twins. So what this digital twin does is that it, based on the existing data set, it tries to construct a simulator model that we expect to replicate the expected noise structure in the upcoming clinical trial. So specifically for this study, the existing data set we use is a roadmap 2.0. This is a data set about cancer patients living in the same dyad. And based on this data set, the digital twin is actually a model, a structured linear model we fit based on this data set. And this model allows us to simulate any potential outcomes given any sequence of interventions. So this simulator model allows us to evaluate, to simulate the outcomes if we had deployed certain algorithms so that we can compare and evaluate those algorithms and select a better one to deploy in the real study. So those are some preliminary results on the improvement on the cumulative adherence based on the digital twin we constructed using Roadmap 2.0 dataset. So here we have 3 candidate algorithms. One is the multi-agent. The second one is multi-agent with a surrogate reward, and the third one is a flattened agent. So the cumulative adherence here is normalized, is scaled based on the sum of the adherence induced by running purely random policy. Okay, so you can see that there is a significant improvement by using multi-agent versus the flattened agent. And there is also a slightly improvement for using a surrogate reward for the multi-agent algorithms. All right, so this would be the end of the talk, and I'm happy to take any questions.
Thank you so much.
Thank you. I was very fascinating. Let me open it up to the audience, what questions or reactions they might have based on what they heard.
Yeah, I know it's a lot of information. Yeah, for details, feel free to check out, a recent paper we published. It has more details.
Let me lead, actually. I was fascinated by your digital twin framework to kind of evaluate candidate reinforcement learning algorithms before deployment. Can you talk a bit more about how you ensure that the digital twin accurately reflects the noise structure and behavioral variability of real-world dyads, especially when working with very limited or noisy observational data?
Yeah, so so one thing we do is like, okay, first of all, this digital twin is based on a physical twin, so it is based on the real data. We're not making up things. So we believe that this is a population that shares a similar structure to the actual target subpopulation that we care about. So this is one thing, and additional care has to be given in the process of constructing this simulator model. So one thing we did was that when we fit those linear models, even though we don't really believe that the system is linear, so we actually record all the residuals generated from fitting those models, and in the real when we simulate the outcomes, we in fact don't use a new noise generated, let's say, from IID Gaussian. We actually inject the residuals we used from learning the model, from fitting the model. So this could potentially capture some of the the non-Markovian structure in the problem, and maybe some of the non-stationarity in the problem. So I think that's also one one decision we made to try to make sure that we can replicate the expected noise structure as we see in the data set.
On a kind of limited similar note, when you are deploying this kind of RL systems in real-world clinical trials, how do you manage uncertainty or data sparsity?
Yeah, I think that's pretty much the main issue that we're dealing with, right? So all of these algorithm design decisions are in fact about managing the data scarcity. And I guess to give a high level of like what are the important decisions that I believe are more relevant, is that we try to keep the model as simple as possible, right? So we barely use the deep models that requires like tons of data set to learn. So pretty much all the models are linear models, and we made sure to only include the relevant variables. And we use high regularization to make sure that the complexity of learning is also reduced. And as I mentioned, most of our algorithms are, let me try to go to that page. Yeah, we always use Bayesian type of algorithms. So Bayesian type of algorithms allows us to incorporate some of the existing knowledge as a prior. So those existing knowledge could be from some existing data set, And we can use this data set to estimate some of the target parameters. And those will be used as a prior mean to warm up the algorithms. So all of these decisions coming up together is a way we constructed to be able to mitigate this issue of having very limited data and having a very noisy environment. So you can see that this is through a sequence of very careful algorithm design decisions.
Very exciting. Let's see any members of our audience who have questions on this very cutting edge work that you are doing, Ziping.
Yeah, thanks. Yeah, it's quite challenging. So,
yes,
nowadays we are actually trying to move towards something a little bit more scalable, because designing a digital twin, it requires a lot of decisions made by scientists. So we are hoping that this more cutting edge, like large scale model and data set could help us to leverage information from other sort of relevant data set. Currently we're only using the data set that we believe are exactly matched to the target clinical trial that we're developing.
Yeah, you're involving dyads in high-stake health behaviors, sensitive health behaviors, and then again looking at distal and direct effects when the immediate observable impact is not quite clear right away. So very
right.
very
so that's a
fascinating.
challenge. Yeah.
Yes.
Yeah. So like how do you bring the very distal outcome you care about into something more immediate so that the agent could learn?
Right. Kind of things that keep Susan awake all night. This is great. Well, it looks like our audience is still digesting that vast landscape you covered. This is great having you, Ziping. We'll have you back as you become faculty and evolve like Walter and Ambuch, and you'll come back.
Great.
We're wish you all the best with your new faculty position. And those of you who have questions, you can always follow up with Ziping directly. So
feel free to reach out to me through
right.
the email.
Right. And the curated lecture will be available for all of you. So having said that, Ziping, thank you again, and look forward to seeing you in person in a couple of months.